Hello, everybody, and welcome. You are joining us for Controlling High Power Laser Processes. This webinar is hosted by Photonics Media and presented by Ophir, and I'm Sarah Weiler. I'm the webinar coordinator at Photonics Media. So in this session, you're going to be hearing from Mark Slutzki, who is product manager for power and energy measurement solutions at Ophir. He's worked with Ophir since 2004, and prior to that, he held similar management positions in the semiconductor and telecom industries. He also served in the military as a research physicist working on special projects for the Israeli Air Force, and his educational background is in electro-optics and applied physics. So today he's going to be talking about how to monitor the parameters of high power laser processes to keep them stable and predictable. If you have any technical issues during the event, I would recommend logging out and logging back in. But if that doesn't fix it, don't worry. This whole session is being recorded. It's going to be online in about a day, and you're going to get links to that in your email inbox, so you won't have to go looking for it. You can ask questions or leave comments for us at any time during the webinar. Just type those into the chat, and we will get to as many questions as we can during today's live Q&A. But if we don't get back to you today, we will send you an email later. So that's all from me. I would like to welcome Mark Slutzki.
Hi, thanks, Sarah. Wait, let's put this into presentation mode. Thanks, Sarah, and thank you everyone for joining us. It's 8 o'clock in the evening over on my corner of the planet. I am having a good strong coffee so that I don't fall asleep in the middle. If you hear me starting to babble, then you'll know that that's probably what the problem is. All right, this is a topic that we work with a lot. Many, I would even say most of the people that we at Ophir work with are not necessarily laser physicists doing research on lasers, but rather professionals working in some application area in which the laser is used as a component, maybe a critical component in making some process happen. And I'm guessing that that might describe many or most of you. So it's for people like you then that I'm hoping to share some insights and some best practices that can help you get the most out of any laser-based process upon which your application might depend. I don't know if I presume you're at least somewhat familiar with Ophir. We were acquired some years back by Newport, and then together with Newport, we became part of MKS Instruments. Our goal here obviously isn't to push any particular products or solutions or anything like that. We're trying to provide, maximally helpful information. So I've tried to keep it as generic as possible. We're also not going into any great engineering depth about the instruments themselves, much as I like talking about them. But you'll appreciate that when I give specific examples of actual instruments and actual solutions, those are going to be Ophir solutions, because those are the ones that I'm qualified to talk about. I hope I found optimum balance between breadth and depth. Not an easy balance to settle on, but I hope it'll turn out to be optimum. All right, so here's what I felt I wanted to cover. We're gonna just do a quick overview, high altitude overview, just so we're on the same page of typical applications for high power lasers. A quick but critically important overview of why, and really just tip of the iceberg, how we measure the main parameters of our lasers. We'll get into some of the interesting challenges that we face when we're trying to monitor the parameters of this kind of laser, and solutions that are out there and in use, some typical and some maybe a little bit novel. And then we'll round off with some best practices and some tips for getting the best bang for your measurement, or whatever the expression is. Okay, so let's begin with the beginning. We'll talk about the nature maybe of modern day applications for high power lasers. All right, research is kind of a trivial one. We're not really going to say too much about that. Most of the drive comes from the interface between research and real life commercially useful applications. Most of the really rapidly progressing ones are probably involving some kind of materials processing, by which I mean using brute force, using the power of a laser beam to burn, zap, vaporize material, often enough very heavy duty material, automotive industry, manufacturing, cutting through big pieces of metal, that sort of thing, automotive industry, aircraft manufacturer, and that kind of thing. Here you can see an aircraft engine. I think this is a turbine blade, if I'm not mistaken. There are a few different types of blades in there. You can see a pattern of cooling holes here that would have been challenging, if not flat out impossible, to produce using classical mechanical production methods. So we're talking about cutting, welding, drilling, and that sort of thing, where we're using thermal effects basically to affect materials. Some pretty exotic applications related to military uses. You hear about these every now and then, directed energy weapons, whether offensive or defensive, as a missile defense thing, where part of the world where I live, that's kind of a interesting and urgently interesting topic. These sort of things you read about every now and then. You keep on hearing that, yeah, it's just about to become field useful, that sort of thing. Sooner or later, it might actually do so. There have been technology demonstrators for the last 10, 15 years. Kilowatts, several kilowatts. But with all the cynicism, some snippets from articles that I took out of the literature somewhere in the past year, that these things are moving forward. The gurus keep on talking about something like 100 kilowatts being the the point at which they become the lasers become actually useful. When they first said that, it probably sounded like science fiction. It's definitely not science fiction anymore. Just briefly, for the sake of completeness, I want to mention a concept called peak power, or instantaneous power, as opposed to average power. A high peak power meaning a relatively high energy pulse with a very short pulse width. So the instantaneous power, remember that power is energy per time, is high. And there are different kinds of effects there that are not necessarily thermal, that can have interesting effects on the material. So here I'm talking about applications where you don't want a lot of average power, because you don't want thermal effects to damage or affect the surrounding material. So micro machining, there's increasingly interesting applications there. An interesting application I came across not that long ago, certain types of marking of syringes. What they do, they use ultra short pulses which change the refractive index of the glass to locally, to give the appearance of printed symbols. And this creates some serious challenging requirements when it comes to measuring them, because the absorber materials that the sensor would be based on need to be optimized for this sort of thing. As I said, I'm just mentioning it for the sake of completeness. Most of our discussion really will be more about high average power lasers. Also, we'll say a few words about high energy pulses, but that's not really going to be the focus. And I gave just one example of that, and there'll be one or two more, again, just for the sake of completeness. Some of the trends that are driving the continuous increase in power of commercially available lasers, the main enabling technology, without a doubt, is fiber lasers. In theory, all you need to do to make a more powerful fiber laser is use a longer fiber. Obviously, like everything, it sounds easy when you say it fast, but the scaling up really is limited more by engineering issues rather than by physics, at least for now. What's pressing the brakes is what I'm calling external issues, things that aren't directly related to the technology itself, to the laser itself, things like managing the heat that gets created, or other things that are application specific, but not necessarily inherent difficulties in terms of making a more powerful laser, with limitations regarding the laser itself. One of the things that's interesting about these mega high power lasers is that these are useful for applications that don't necessarily need 80 kilowatts of power per se. But you have an 80 kilowatt laser, you can split the beam among multiple parallel processing stations, each of which might only need a couple of kilowatts, but because all those beams are coming from one source, then there's a lot more uniformity and much better control over the parameters of the beams and uniformity across these multiple parallel workstations. And that can be a critical issue sometimes. And we'll see one example of that in a case study that I'm going to show you in a couple of minutes. Okay, so let's talk a little bit about why and how. Very high altitude, as I said, we're not going into great engineering depth in terms of the instruments and the measurement technology, but just enough to make the rest of our conversation meaningful. So let's begin with the why. I trust I don't need to work too hard to convince anybody of the why, but just let's kind of get this, so we have our eye on the ball. Here's a schematic drawing, pardon my artistic skills or lack thereof, of a typical materials processing application, a very generic one. Okay, you have a beam, you have some kind of focusing optics, and then the beam gets focused, and if nothing stops it along the way, it'll continue past focus and defocus. In order to melt, vaporize, or otherwise zap the given material, we want a beam with a given power and of course a given wavelength to be focused down to a given diameter such that the power density is high enough to do the work. So here we see the space. Here, I hope you can see my cursor. Here we see the space within which we have the required power density. I'm dreadfully oversimplifying this, I know. Now, we design and program the system, let's say a laser cutting system or what have you, so that the user punches in a given application and the system sets up the exact electrical parameters such that a beam with the exact optical parameters will be generated. But what happens when, let's say, the power drift, maybe due to aging of components, or say heating effects change the optical characteristics of the focal lens and the focus shifts? We can suddenly find ourselves with the target surface, the workpiece, outside the space within which the power density is high enough to do the work, or still within that space, but the shape of the drilled hole might be different because we're not in the location of the waste that we thought we were in. Whoops, I ran ahead of myself. Parameters that are not controlled can change what the process is doing and where it's doing it. And that can make your process unpredictable. In the case of an industrial commercial process, it can eat into the profits that it's supposed to be generating for you. If we're talking about medical applications, it's easy to appreciate the potential consequences. All right, I trust I don't need to belabor this point. Now I can run ahead of myself. Briefly, how we measure. We're not going to go into the engineering behind every possible method, but again, just to give meaning to the rest of our conversation. So here, again, a generic type of a laser power sensor for the sort of moderate and high power levels that we're talking about when we're talking about high power industrial laser beam applications. So here's a pretty typical sensing element of a laser power sensor. You've got a metal disc, you've got a thermopile ring. If you're not familiar with that, don't worry, it detects heat flow. Okay, so in this case, we're looking at the side of that disc that's inside the body of the sensor, and the beam would be coming towards you from behind the plane of your screen. Right, so the laser beam would get absorbed by a suitable absorbing layer on that side of the disc. The resulting heat spreads radially outward, flows past the thermopile ring, and out comes an electrical signal, voltage, current, that is proportional to the parameter we're trying to measure, let's say power. And then, of course, that heat, the body of the sensor needs to be designed in a way that can, suitably get rid of that heat at least as fast as it's coming in. Now, as I said, this is simple and generic. There are somewhat specialized configurations for specific needs. We're going to touch on some of them as they come up. There are other parameters that sometimes are of significance in some applications. I mentioned energy briefly. Sometimes it's the pulse energy that makes the process happen. Sometimes we work in single shot energy mode, meaning we fire one pulse and then we wait and check the results. A lot of welding applications work that way. Sometimes we use repetitively pulsed beams. Usually those are not so high in average power. Different kind of sensing technology for measuring those. We're not really going to get into that. In many applications, the spatial profile of the beam, which means the spatial distribution of energy in the beam's cross-section, can be critical. It affects the focusability of the beam, if I can coin that as a word, and the shape of the focal spot, and therefore the shape of the resulting cut, hole, weld, zap, or whatever. As you probably know, we have solutions for beam profiling of high power beams way beyond the scope of today's discussion, but I just had to mention it. Sometimes it's enough to measure not necessarily a full-blown beam profile, but we just want to know where the beam is. So there are sensors that can measure power and the position of the beam centroid, and sometimes, depending on A, B, C, D, E, the size as well. It's kind of a poor man's beam profiler. There are those out there as well. If you're dealing with a high power beam and you're sampling off a small fraction of it to be measured, you want to be sure that you know what's going to be happening to the rest of the beam. So sometimes we're talking about inline monitoring of a process without interrupting the process, then that's great. Otherwise, we need to provide some kind of a beam dump. You might use your colleague who's competing with you for, project success, across the lab, but we're not going to go there. We're just going to mention that there are commercially available beam dumps that usually provide better solutions. Okay, here we see a typical laser power measuring instrument. So for our purposes, we're going to say that it consists of two parts. There's the laser facing part, which is the sensor that absorbs the beam and produces a signal that somehow or other represents the parameter we want to measure. And then there's an output. So in this photo, the output is a device. It's a handheld or desktop meter. Keep in mind that the output might not be a device. The output could just as easily be software running on a PC or something like that. I'm only mentioning this because we will also be looking at all-in-one solutions in a couple of minutes. Very often the sensor is used, and I think this is already touching on something of more central interest to our topic, is used to provide real-time feedback control to the laser built into an application, into a process. In some applications, this sort of self-calibration of the laser system is performed periodically, say once a day, once an hour, once an X, or maybe before each new workpiece or run of the process as relevant. We can have built-in monitoring that samples a percentage of the beam full time. In the big gas lasers, you can have a rear leak sensor behind the rear mirror. You can use a mirror that samples the beam in time. When we want to take a measurement, the mirror moves into place and 100% or 50 or whatever percent of the beam gets deflected into the sensor. The rest continues, or sometimes most of the time the mirror can be in place. Every configuration, again, depends on the needs and the nature of the specific application. And so that sensor can be integrated inside a host system on an OEM basis. It can be used externally, moved into and out of the beam for the purpose of taking a measurement and then getting out of the way, everything or combinations thereof. We have many customers who use what some of them at least call the calibration port. It's a hole on the side panel of the machine, the laser drilling machine or whatever. And once every X, the user takes the handpiece, puts it into the hole, into this calibration port, fires the laser. A built-in sensor measures the power of the beam, compares it to the power that it was expecting to receive based on the software commands, based on the electrical drive current that it was pushing through the laser, and so on. And as required, it can make internal adjustments and calibrate itself so that emerging from the handpiece, and meaning arriving at the target plane, the target surface, will be exactly the power that the designer of the process expected to be arriving there. Sometimes we'll use this method, sometimes we'll use a small sensor integrated inside that's sampling a fraction of the beam right as it comes out of the laser source itself. And there are trade-offs here that the so-called owner of the application will need to make using the small internal sensor that's sampling just a small fraction of what's coming out of the laser source. That lets you use a cheaper and smaller and simpler sensor. On the other hand, using a full-blown higher power sensor at the target surface, actually seeing what's really arriving at the target surface, taking into account other things that might be happening along the way downstream from the laser source itself. And again, each process owner would, work out these trade-offs in the best way that's suitable for the needs of the application. Just a side point, since I mentioned before, measuring the power that's arriving at the work surface, it's important to stress. I think this is probably well known, but you'd be surprised at how often even seasoned professionals miss this. You don't want to measure the power at the same plane as your work happens. If your work consists of very high power density drilling a hole through sheet metal, then if you put your sensor there, you're going to be having very high power density drilling a hole through your sensor. Not a good thing if you want to use that sensor more than once. It's the same number of watts in focus as out of focus, just not the same number of watts per square centimeter. So you want to find a location where the beam is defocused and do the measuring there. And you want to make sure that there is somewhere where the power density is safely below the limits that are specified in the sensor's data sheet. And just as a side point, but an interesting one, not everyone knows that all other things being equal, where practical, it's preferable to measure before focus rather than after focus, as I thought this was very cool. At the focal spot, there may sometimes be losses caused by photoacoustic shockwave effects. All right, tell me that's not cool. All right, well, sometimes I find something very cool and I try to tell my kids and they roll their eyes and look at me and, you're being a nerd, Dad. Yeah, I know. Being a nerd is cool nowadays, but okay, whatever. I'm sure many people attending a webinar like this probably have had that experience. All right, question we get asked all the time. Okay, you convinced me. I need to somehow keep track of what my laser power looks like. And again, I'm gonna keep on saying power, but I mean power or energy or whatever parameter it is. So why don't I just why do I need a full-blown instrument with software and calibrated and all the other stuff? I can just buy a photodiode for less than $1 in some online catalog. I've got engineers, I am an engineer, can put together an amplifier. Why is that not good enough? Why, so, okay, you can. So a number of things you might need to keep in mind though, putting a small photodiode right near the laser, you'll be catching changes that originate at the laser, but you won't catch changes that happen because of something that happened farther downstream. You'll probably need to add a lot of attenuation if you don't want to, saturate and maybe vaporize your photodiode, and that it pretty certainly will introduce artifacts into your measurements. You'll need to take into account dependence of the raw photodiode's sensitivity to temperature and frequency and other parameters like that. There are going to be variations from batch to batch if you're buying raw detector elements. Many applications, not all, but many will need some kind of a quantified absolute accuracy to some degree. Addressing these issues can be done, but they will involve cost. Engineering hours cost. Making, what may turn into a photonics project will cost. It might be a cost that doesn't show up on the bill of materials of the bottom line system, but it's there. That's such a common question. We've even got a video and a blog about it on our website. All right, let me just share with you a quick case study. This is on our website. A couple of years ago, a medical customer actually manufactures implantable medical devices. And this particular device, I have no clue what it is, was being produced simultaneously at 2 different facilities of this company. Same setup, same laser, same process, same everything. The parts coming out of one facility were good. Parts coming out of the other facility kept on failing. Luckily, the failures would be caught at inspection and not farther down line like in a patient. They couldn't figure out what was the difference because the processes were the same, or certainly were designed to be the same and were supposed to be the same. So they called us to help them out. And even though the processes looked the same on paper and the equipment was the same, when we started taking detailed measurements of the power, and in this case, more specifically, the beam profile, it turned out that they were not the same. In one of the facilities, something in the optical alignment had shifted, and that was that. Once they found that, then fixing the problem was easy. So that was a good one. Okay, let's talk about some challenges involved in monitoring the performance of these high power lasers. Some of the challenges are in the user's court, some of them are in the manufacturer's court like us, but it's interesting for you to be aware of them and how they're dealt with. So we'll start with the challenges and then we'll say a few things about solutions that are out there. In no particular order, maybe. First challenge we're going to talk about is cooling. High power laser beam carries high power. And when a sensor absorbs and measures that beam, the optical power of the beam turns into heat, which we got to remove from the sensor at least as fast as it comes in. Otherwise, the heat's going to start building up. Temperature in the sensor is going to go up, sorry. And eventually, some element of the sensor is going to fail. For that kind of failure mode of overheating, the first point of failure is usually one of the thermopile junctions. So for lower powers, conduction of heat from the sensor body out into the air is probably good enough. Beyond a few tens of watts, we need to help that along by adding a fan. And you'll probably notice in images in our catalog and others that the bodies of the sensors are designed as some sort of a heat sink. And beyond that, then usually we're going to need water cooling. I just mentioned damaging a sensor by overloading it. There are many ways to damage a sensor. One is too much power. No measuring device likes to be overloaded. Another much more commonly occurring one is too high power density. Even if you've got relatively low power, but focusing that down to a small enough spot can be used in marking serial numbers in jet engine blades or blasting holes in a laser power sensor. So you want to kind of keep track of what the data sheets of the sensors specify as the maximum power density or damage threshold, the maximum power density above which the sensor is in danger of localized laser burn damage. I'm sure that you've heard stories of mischievous young boys who are going to grow up to be physicists one day, going out into the garden on a sunny day with a magnifying glass and causing localized burn damage to innocent passing insects. I've heard this about other mischievous boys who were growing up to be physicists, other boys, of course. It's important to note, very important to note, that the damage threshold, that maximum power density, is not one fixed number. It changes. It actually depends on the power level. And a picture is worth 1,000 words, so I'm going to show you why that is. Our x-axis is my absorber, and the y-axis is temperature. A given absorber type, okay, low power beam, at the spot where the beam's being absorbed, I'm getting kind of hot. As the heat moves away, the area surrounding that spot is quite warm. And as I move farther away, the material becomes cooler. Here's a screenshot from the thermal simulation software that our engineers use to design these things. Now let's take that same absorber, but now let's use it to measure a high power beam. So high power beam, the spot at which the beam is being absorbed is not kind of hot, it's really hot. And the area around it is not warm, it's very hot. And I have to move much farther away before I can even start using words like somewhat hot or warm. There's just a lot more heat being generated here. So the area around the absorption spot is much hotter. So the new heat that keeps being generated as more power keeps coming in is going to have a much more difficult time getting out of the way. So the area around that spot is going to be much hotter over a much wider area. And here's what the thermal simulation looks like for that. So you can appreciate it'll take way fewer watts per square centimeter to cause the material to heat up to the point where it's going to burn and get damaged. So we specify in the Ophir sensor data sheets, we always specify the damage threshold of a sensor at the highest power for which the sensor is rated, so that that number will actually mean something to you. Another challenge is backscatter. Typical thermal absorbers on sensors, they absorb around 90% plus minus, a little more, a little less, depending on wavelength. The remaining 10% gets reflected back out. Usually it's a very diffuse reflection, so you can see these things don't look shiny, they've got a matte finish. Not a big deal, but if you're talking about, let's say, 50 kilowatts, that means 5 kilowatts of power are being, backscattered back out into the, back out into the room, and obviously that can pose a safety hazard to personnel in the room and to equipment. Another challenge, keeping the measurement instrument technology suitable for industrial environments. And we're going to break that down into two different issues. One is footprint. Okay, I'm sure you've seen, certainly think of a wafer fab or any other kind of very modern, advanced technology production factory floor. Real estate is really valuable there, and you think 10 times before deciding to adopt some kind of a monitoring technology if it's going to take up a significant amount of floor space or bench space or anything like that. So you want the instruments to take up, to have a minimum footprint. And the second issue is these things usually don't stand alone in a room. They're usually part of a whole production facility where there are many stations at which the same process or other processes are going on. And it's not always something, not always possible or practical to have an operator walk in there and start pressing buttons. Usually you want the instrument to be, connected to a network that automatically is controlling the whole production environment, and the solutions used need to be suitable for that. And another issue is ever increasing powers. How scalable is the technology? You're using, 20 kilowatt beam in the process that you're doing now. In 2 years, that might double. Are you going to need to buy a whole new type of measurement instrument with new software, new whatever? Or will you just need maybe to upgrade to slightly, a higher power rated sensor? How scalable is the technology that's being used? All right, let's talk about solutions now. So just reminder, these were the issues that we just mentioned. The challenges rather: cooling, preventing damage, minimizing backscatter, adaptability, suitability to industrial environments, both in terms of footprint and in terms of integrated into a factory network, and scaling up of the measurement technology as the laser powers scale up, over the years. So let's go in order. Cooling. So I mentioned before that for powers above a couple hundred watts, usually fan cooling gets dropped and we go to water cooling. Here you see a fan-cooled sensor for just over a kilowatt. This is an Ophir sensor. As far as I know, it's the only fan-cooled sensor for that kind of power range, but usually for those kind of power levels, water cooling is the method of choice. So here you see a couple of different kinds of water-cooled sensors. We're going to see two different configurations. This one is based on a standard radial thermopile like you saw before. Laser beam enters into the sensor's aperture. This happens to be a 5 kilowatt model. You can see the water connectors for the cooling water input and output. That was the generic type that we discussed before. There's another approach, same physics but different approach, and that's using a calorimetric measurement method. We're starting now to see some of those so-called specialized configurations that I mentioned at the beginning. There are some cooler ones coming up. Sorry, pun somewhat intended. We're going to have a few words to say, some important tips, pointers about the cooling water. Just hang on a sec. And what happens in a calorimetric, it's almost past my bedtime. The calorimetric method of measurement is that we're measuring not the heat flow across the thermopile, but the temperature rise of the coolant. Let's say the difference in temperature of the cooling water coming in and going out. We might, generally, if we're using that method, we'll also have a device built in that measures the flow rate of the cooling water, and combining those two pieces of information, we can derive the power. Other probes, where we expose the probe to the laser beam for a very specific amount of time and measure the temperature increase of the probe. So in some industrial applications, that method gets used. So here you see a few different models: a 15 kilowatt sensor with a protective cover with a painted target for alignment, 16 kilowatt sensor, 30 kilowatt sensor. This is pretty massive. So you can see that its mounting base is suitably designed. I just want to say a couple words about the 16 kilowatt model because there's one interesting feature that it has. And that interesting feature is this module over here. It's a alarm and interlock module, which the user can connect to the laser, and it monitors the cooling water the flow and the temperature, and it can be set up to automatically disable the laser if it detects that something has gone wrong with the water cooling, so that the sensor doesn't very quickly overheat and melt or anything like that. Okay, the next challenge that we talked about is preventing damage. So one way to prevent damage is making sure that you're using your sensor safely within the limits defined in the data sheet. But there are some things that we do to help you prevent damage. And one of the most obvious ones is we're constantly working, and so are all other manufacturers who make these kind of measurement devices, constantly working to improve the absorber materials. These are specialized materials. It's a never-ending effort, to make, better, tougher, more resilient absorber materials that have good spectral characteristics, that can handle high average power densities, that can handle long pulses, short pulses. There's always trade-offs. So here, for example, this sensor uses an absorber that we developed a couple of years ago. We call it LP2. LP stands for long pulse. Short pulses, long pulses, meaning nanoseconds or milliseconds. Very, very different behaviors. There's always a trade-off. So here you see a 1 kilowatt sensor, water cooled, and it has a damage threshold, the maximum average power at 1,000 watts at the full power of 10 kilowatts per square centimeter. Now, just if you're not very familiar with these, I'll tell you that's an impressive number. That's a really good number for working at that power level. And when working with long pulses in the millisecond range, let's say welding applications or whatever, 400 joules per square centimeter. Again, that's a good number, okay? For very high powers, there's another trick we use besides just designing better and better and better absorbers is, I wish we could claim credit for this, but this is a standard trick used all across the industry, to add a reflective cone. I don't know if you can see it in there, but basically for a given, as we just saw, as the power goes up, the damage threshold goes down. So for a given power and power density, we're going to reach a limit at some point. What we do here is, instead of that being the absorber, the cylindrical wall around it is the absorber, perpendicular now to the plane of your screen. And the beam comes down, hits that reflective cone, and gets reflected radially outward with a divergence angle, so that by the time it reaches the absorber, it has expanded. So the power density has gone down. So that enables the sensor to handle higher power densities than it otherwise would have. And you can see this sensor at 10 kilowatts actually has the same damage threshold, 10 kilowatts per square centimeter, as this one had at 1 kilowatt, and that's because of the reflective cone. So there are all sorts of tricks of that nature. Next issue, backscatter. Okay, so there's an accessory that we have at Ophir. Called the scatter shield. It's an accessory that screws onto the front. I don't know if you can make it out in the image here, but there's some backward facing ridges, and that 10% of backscattered light that reflects off the absorber, some of it hits the walls of that snout, and much of that then gets re-reflected back in for a second go. So much less. This actually cuts down backscatter by around 70%. Now, of course, because more light for a given beam is actually getting into the sensor, because some of that light gets a second chance, the meter will need to know that the scatter shield has been added. There needs to be a separate calibration factor for the scatter shield in condition. Okay, industrial environments, footprint. When you're dealing with high powers at ongoing constant exposure, you need a big water-cooled sensor. There's got to be room for the water cooling channels and so on. But in many applications, you can get away with taking a measurement for a few seconds at a time, once every so-and-so. So we have a trick that we have in Ophir. We call this pulsed power mode. The basic idea is that we fire the laser for a short, precisely controlled time. We pretend that that's a pulse, and we measure that single shot pulse's energy. And then we divide by the time, by the duration of that exposure, the pulse width, if you will, and energy divided by time gives us the power in that beam. Now that can obviously be done offline manually, or it can be done by having a suitable function in the instrument. The instrument can be designed to then prompt the user to enter the known exposure time. I call that semi-automatic, or the instrument can be completely self-contained and have in it a fast photodiode that'll measure the exposure time, and then it'll do it all automatically. I was debating with myself whether just to show you, I'll just show you a few seconds of what that actually looks like. I hope you can see this. This is an Ophir meter in that mode. Here, pulse width, the user entered that, and we're getting a power reading. Here, that wasn't too bad. Okay, just to convince you that that was real. Okay, so we have a bunch of regular moderate power sensors to which we gave particularly high energy scales for exactly this purpose. And that lets you use small moderate power sensors to measure very high power beams. Then you give them some time to cool off, because they're not able to withstand that power level continuously, but that's okay in this kind of mode. Let's look at some self-contained instruments that are completely standalone. Regarding the challenges of making a monitoring solution suitable for industrial environments, besides footprint, we also mentioned factory integration. So here you see a completely self-contained instrument. It's got that sensor built in, small. This is 20 centimeters long, industrial body, and this is designed to be integrated into a factory network. Nobody needs to come and press any buttons. You can see that there's industrial connectors, actually 2 of each. One for power, one for communication, so it can be connected in a daisy chain ring, and the factory floor server will send an instruction to open the protective cover to expose the sensor. When we want to take a measurement, it takes a measurement, it closes, moves out of the way, and the robot then moves the laser head over the workpiece and starts to work. Very nice solution. And then there's models with Profinet or EtherCAT or Ethernet over IP, all sorts of different protocols depending on the needs. A very common industrial scenario involves high power measurements in a tight or inaccessible space. There's no option for fan cooling or water cooling. There's no way anybody's going to be able to come up and press buttons. Think of an additive manufacturing chamber as an excellent example of this. So here you see a self-contained instrument that's completely self-contained, not even a cable. So you can stick this into the chamber, close the door, look through the window, and you can see what's on the screen. It can be set up using front panel buttons, or you can communicate with it wirelessly through a Bluetooth interface. And this thing, small, it can fit in the palm of your hand, right? And it can measure up to, in this case, up to 8 kilowatts for this particular device. 7 by 7 by 8 centimeters. And again, it uses that same short exposure method of measuring high power. So no water cooling, dust proof, splash proof, and so on. Okay, I was going to explain the concept, but I think I actually already did. These last 2 instruments that we just saw are what I referred to earlier as fully automatic. They both have in them a fast photodiode that measures the exposure time, the pulse width, if you will, and automatically and directly outputs the measurement in terms of power. So here you see a regular sensor connected to a meter. That would be what I called semi-automatic, as you just saw in that little video. That was a different instrument, or one of these things where it's fully automatic. Last issue, measuring extremely high power, scaling up using the same technology, the same software, compatible with the same output instruments, the same meters and everything like that. What you see here is the first commercially available sensor for measuring up to 120 kilowatts. When we first came out with this a couple of years back, maybe military and really high-end research, but very quickly it became, I won't say standard everyday industrial use, but approaching that. It looks big. This is 50 centimeters by 50 centimeters desktop, and it's almost like a black body. So less than 1% of the incoming power backscatters out, which is a good thing when you're talking about 100 kilowatts. And the measurement module here does what I mentioned earlier. It measures the temperature increase of the cooling water and the water flow rate. And from those two pieces of information, it gives the power in the beam. Here you see it measuring at a customer location, a 100 kilowatt fiber laser. And the beam watch, I can't not mention this. It's a non-contact high power beam analyzer that Ophir Spiricon came up with a couple years ago. It's based on Rayleigh scattering, where some of the light from the high intensity beam is, all right, this is cool, is scattered off air molecules. And a camera uses that light to capture and then analyze an image of the beam waste without coming into contact with the beam. That's cool. I'm not even gonna, I never even tried to tell my kids about that one. Okay, let's talk about a few best practices, some kind of, black belt tips to get the best performance and the most successful and correct and accurate monitoring of the right parameters in your applications. Probably the most obvious one, and as obvious as it is, I cannot overemphasize it, is to keep your sensor clean. Okay, here you see a sensor. The sensor apparently must have had some organic stuff splashed on it, but that stuff didn't get cleaned off, and the next exposure to a laser beam, it got burned on. This can't be cleaned. That sensor needs a pretty expensive disc replacement. Had it been cleaned before exposing it to another laser beam, it probably could have been cleaned off very easily with a soft tissue and some suitable cleaning agent. And depending on the sensor type, some absorbers are delicate and no cleaning agent, just clean air below, whatever, there are instructions for all of those things. We actually offer for some of the industrial high power sensors, protective housing with the, with the open automatic closed shutter. A TTL pulse tells it to open when it wants to take a measurement, and then it springs closed again to protect the sensor from process debris. Prevention is always way better than repair, as in so many things in life. Sorry, I pressed twice. In general, as far as possible, you want to keep your beam centered. When we calibrate these sensors, we keep the beam centered. So if when you measure with these sensors, you keep the beam centered, you've just eliminated tolerance on surface uniformity as a possible variable that could affect the accuracy. Not the end of the world. The tolerance on surface uniformity is usually 1 or 2%, but still, every percent counts. Very important if you're using one of those higher power sensors with a reflective cone. To avoid damage, first of all, it's even more important to keep the beam centered, because otherwise it might not all hit the cone, and then it'll cause damage if it hits any part of the absorber before it has been expanded by being reflected off that cone. And also keep it properly aligned for the same reason. And the data sheets usually specify the maximum angle beyond which it might miss the cone or hit the cone but not get uniformly radially reflected. And again, some spots on the absorber will then receive a non-uniformly high local power density and potentially get damaged. Okay, thermal offset. In general, these sensors measure laser power by measuring the heat flow that results from absorbing the laser beam. When the sensor gets hot, you start running into questions of, am I measuring heat that's caused by absorbing a laser beam and I want to measure that heat, or am I maybe measuring heat that's coming from something else? So most power meters have an offset function. So if you know that there's a heat source right nearby, you block your laser beam. The reading you're getting now is an unwanted offset, like a DC level. You press that offset button, and the instrument will automatically subtract that from all subsequent measurements. So when you've got a fixed, steady heat or light source in the background, that's a great function to use. But sometimes that's not a good idea. For example, let's say you bring your sensor from a hot car into an air-conditioned lab. So now the sensor is hotter than the air around it. It's going to start giving off heat and cooling down, which means there's heat flowing inside the sensor towards outside the sensor. And that's going to cause an offset reading even with no laser on. So you might be tempted to press the offset button to cancel out that offset. The problem with doing that is, though, that as the sensor continues to cool down, the actual offset resulting from the temperature difference between the sensor and the air is going to start to drop. But the meter is going to continue subtracting that original offset from all subsequent readings, and so your reading is going to become increasingly wrong. So you don't want to start working. You have no shortcut, really. You want to wait until the sensor is in thermal equilibrium with the environment. And then if you have some kind of a thermal or optical offset, then you can press the offset button, because now you're going to be subtracting a known, steady, bad offset. Offset that results from heating of the sensor when the beam is on, by the way, is built into our calibration. So zero the sensor only when, meaning offset, only when it's in thermal equilibrium with the environment. Some really important tips with water cooling, and then we're gonna summarize. Very, very important, and we've learned this from a lot of bitter experience of our own and of many of our customers. Turn the water flow of the cooling water on before you turn on the laser. With high power beams, it doesn't take very many seconds to heat the laser, to heat your sensor up to the point of zapping it, if it's going to take a few seconds after turning the laser on before the cooling water starts flowing through the water channels. Turn the water flow on before turning on the laser. I could say that 10 more times, and the guys who repair these things when they come in will still tell me that I didn't say it enough. We often get asked about water types. I'm not going to go into the details, but one question that comes up super often is regarding DI, deionized water. It's got a bad reputation. Our experience and our analysis, we've got a lot of experience with this, is that DI water is good. It's better than using tap water, because tap water, you just don't know what ions are present in the water, what ions are in your city water. It could vary from day to day and from city to city. And a wrong ion mix could lead to corrosion. So DI water is good as long as you're keeping a neutral pH. You might need to use some additives to the water to do that. Water temperature is important. That's specified in our data sheets. More important than the temperature is the stability of the temperature. If the temperature of the cooling water fluctuates, it's going to cause heat flow in the sensor. It doesn't take much to get picked up and register erroneously as laser power. So the temperature, the flow rate, the pressure, we've got all of these in the data sheets. Standard procedure, you'll want to check that. We've got an excellent white paper on our website that's not Ophir specific. I'm going to show you where that is in a second. We often get asked, well, what cooling capacity should my chiller have? Our sensors are quite forgiving of chillers. We don't really, the sensor doesn't care too much about the details of the chiller, as long as the chiller has the capacity to take out as much heat as is coming in. So if you're going to be using this water-cooled sensor to measure a 30 kilowatt beam, you want to use a chiller that can extract 30 kilowatts of heat from the water. If you can, I mentioned stability, alarm interlock. I showed you one model that has that. Very detailed guide. Go to our website, ophiropt.com. You go to the Photonics section. You can go to the MKS website and search our knowledge center for a white paper called, you'll remember this title, How to Use Ophir Water-Cooled Sensors. I should just mention, we offer at Ophir, we also offer a corrosion-proof sensor in which only copper and non-metallic materials come into contact with the water. So if you have reason to suspect that you are at risk of corrosion issues, you might want to consider that. In summary, so we talked about today's high-power laser applications, very briefly touched on why, and a little less briefly on how we do the measuring. We talked about the challenges, cooling, avoiding damage, minimizing backscatter, footprint and integrate, keeping the footprint down and capability of being integrated into a factory floor network so that we have maximum suitability for industrial environments, and scalability as laser, keeping up with the ever increasing powers available with today's laser systems. And we talked about a few best practices and tips. Keep your sensor clean, only subtract thermal offset when the sensor is in thermal equilibrium with the environment, and some tips about water cooling, most importantly, knowing where that white paper is, how to use Ophir water-cooled sensors. That is, okay, I squeezed a lot of information. I think I went a little bit over the time that I wanted to go in. I think we still have some time for questions. Sarah, I'll turn it back over to you.
All right, thank you so much, Mark. That was terrific. We do have about 5 minutes to take questions, so I'm going to take a few here. And if you think of more later, feel free to email us, to everyone in the audience. So you mentioned an option of integrating a power sensor into a system to help provide feedback control to the laser. To do that in my case, I would need some pretty specific mechanical dimensions, and I needed to be controlled by my system software and so on. How do I go about this? None of the catalog instruments looks like a fit.
Okay. Yeah, that's also something that we get asked very often. In these kind of industrial applications, that's not unusual. So certainly at Ophir, and I would imagine at other instrument manufacturers as well, we do a lot of customization for exactly this sort of need. Depending on the specifics, we can work together with you to put together an optimum solution, either a slight modification of an existing device or something completely custom designed from scratch, from the ground up. Now, obviously, if it's a one-off need that's far removed from anything standard and it's just for a research project, then it might not make sense neither for you nor for us to go that route. But let's see, and we might instead, in such cases, we might help you identify the closest standard solution that, as far as possible, helps you solve the problem. The first step would basically be just to, contact us, and we'll start the conversation going and see how we can best help you.
Could you please repeat the exact effect you were talking about concerning acoustic wave generation in a material when the beam is out of focus?
Oh, okay. It's when the beam is in focus. I actually read about that not long ago. Basically, when you've got very high peak power, meaning very high instantaneous power, it could be a not such high energy pulse, but with a pulse width of some femtoseconds, which we're seeing more and more of. So the extremely high peak power has all sorts of nonlinear effects that are not thermal. We're not talking about burning, but we are talking about, let's say, ablating a surface of, let's say, of a sensor's absorber, or even, having nonlinear effects, in the air or in crystalline materials. So we have found, and I've actually read a little bit about this. I don't have enough of the knowledge in my head right now to even pretend to go into the details. But when you've got a small spot, you've got a high, the pulse energies, we could be talking about a few millijoules with pulse widths of a few femtoseconds or even picoseconds. Nowadays, picoseconds are not considered so extremely short, but we're getting a lot more femtosecond stuff now. A few millijoules with femtosecond pulse widths, we could easily reach into the gigawatts of instantaneous power. And when all of that gets focused down into a small spot, then in that focal spot in the air, you've got the air ionizing, you've got a momentary, like a few picoseconds long flash of extreme energy zapping the air becomes conductive, all sorts of funny things happen. I just saw, I read something not that long ago, I actually think it might have been photonic spectra even, where the military was experimenting with firing a pulse of I think it was like 100 millijoules, femtoseconds, and it ionizes the air as it travels through it, and it leaves you with a long channel of conductive air just through free space. And immediately after firing the pulse, they fired like an electrical current, and it zaps a vehicle on the road or something like that, which is pretty bizarre. So when you get this small, very short time, very high intensity flash of ionized air, you get thermal shock waves radiating out of there, and some of the light actually can get scattered because of that, and you'll measure less on the far side of that spot than if you measured on the near side of that spot. That's another one of these things that I'm not even going to bother telling my kids about, but that I just found really incredibly cool.
All right, well, thank you so much. That's all we have time for now. Thank you everyone for your questions. Again, if you think of another one, feel free to email us. I know Mark's got his email right on the screen, but you can also reach out to webinar@photonics.com, which is webinar@photonics.com. And one more reminder, this whole session was recorded. It's going to be online very soon, and you're going to get links to that in your email inbox. So thank you so much to our presenter one more time, Mark Slutzki, Product Manager for Power and Energy Measurement Solutions at Ophir. And thank you everyone for participating. This has been Controlling High Power Laser Processes, which is presented by Ophir and hosted by Photonics Media. Thank you so much, everyone.
Thanks, Sarah. Thanks, everyone.